Hello, welcome again to another session of Everyday Mathematics. So the slogan here is that we do enjoy solving the harder problems. We also appreciate and see the beauty in the simpler problems. So today we are still in the 2022 MIT Integration B semifinals. Our problem comes from semifinals number 2, problem number 3. Which is the integral of 1 over x squared minus 2x cotangent or cot x plus cosecant or cosec squared x. So this is a very interesting problem. It does involve a new theorem that we'll be introducing to be able to solve it. But before we delve into the solution, just a quick shout out. Thanks to our subscribers. We do encourage us to keep chugging along. For those of you who are here for the first time, we also encourage you to subscribe. If you are here for a second or third or fourth time and haven't subscribed, please do subscribe. So moving forward to the solution, the first thing that I would like to do is just find the relationship between cosec and cot. So as you know, this major identity of sine squared a plus cosine squared a being equal to 1. When you divide through by sine squared a, you get 1 plus cos squared a over sine squared a, which is equals to 1 over sine squared a. Now that means that 1 plus cot squared a is equals to cosec squared of a. So we can place in this integrand, in place of cosec squared x, we can place in 1 plus cot squared x. And that's exactly what we're going to begin with. It seems obvious, but I just wanted to begin with that preamble. So we have the integration of 1 over x squared minus 2x cot x plus 1 plus cot squared x. Now we can rearrange a little bit, so bringing cot closer here, and I haven't really done anything there, but we bring cot squared x closer, and we can see that these first 3 terms in the denominator come from a binomial expansion of x and cot x. So we'll go ahead and express that in form of that binomial expansion, binomial expression. So we have 1 over x minus cot x squared plus 1. And that expression is where now we can now bring in this new theorem to try and solve this equation. So we'll use Glasser's master theorem, which states that if AI and BI are real numbers, and that we have a function u is equals to x minus a minus a series of x as shown here, then the principal value of the integral of fu, a function whose variable is u, is, if you integrate that from negative infinity to infinity, that integral is equal to the principal value of the same function, but this time x being the primary variable under consideration. So what that means, to explain, So we have an integrand 1 over, and if we consider x minus cot x as our u, this function is 1 over u squared plus 1, right? Now, the integral of this 1 over u squared plus 1, with cotangent being there, is the same as the integral of now 1 over x squared plus 1. And this obviously is limited to when we have the limits minus infinity and positive infinity as the upper limit. Now we know cotangent can be expressed as a series form, really to satisfy what Glasser's-Master theorem is talking about. So essentially, what that means is 1 over x minus cot x squared plus 1 integrated from minus infinity to positive infinity is the same as the integration of minus infinity to infinity of 1 over x squared plus 1. And so for those of us who know this integral here, this is the same as arctangent, obviously with our limits under consideration. So when we substitute in the limits, that's the same as pi over 2 for the positive, as x tends to positive infinity. Arctangent of x tends to pi over 2, and as x tends to negative infinity, arctangent of that tends to pi over 2. So the answer is pi. Now, I don't know whether there is any other method that could have been used to solve this integral, but it just did require knowledge of Glasser's-Master's theorem. I think that was the bare minimum that was required to solve this problem. So thank you again for hanging out with us. This obviously has been an interesting problem to solve. Until next time, thank you, and please subscribe to our channel.